So this presentation will be about online system identification through active causal learning. And in particular, the problem that we consider in this work is to identify a mathematical model of a network system that can allow us to reason about causal effects, such as the effect of resource allocation on response time, or the effect of network configuration on service availability, or the effect of a link failure on network performance. All of which are typical questions that arise in the operation of a network system. And by being able to reason about these causal effects and maybe also predict them, we can achieve more reliable operation of the system. In fact, one could say that as much as 30% of the outages that we see in practice could in principle be avoided by having an accurate causal model of the system. And I'm not sure if you were impacted by this, but very recently there was a global outage that affected all of Microsoft services. And this outage was caused by a configuration change that had an unintended causal effect on the rest of the system. Now, in this particular example, the configuration change was made by a human operator, but you can also imagine that in the coming years, many of these updates and configuration changes are going to be automated through autonomous agents. And then it becomes even more apparent and even more clear, at least to me, that we will need to have some form of a causal model of the system in order to achieve reliable operation and predictable service quality. So motivated by all of these potential benefits and use cases of a causal model, we have developed a new method for learning a causal model online based on system measurements, which is illustrated in this figure here. So at the center, we have our network system. And during operation of this system, we are monitoring various system variables, like the CPU utilization, the load, the response time, the memory usage, etc. And through this monitoring, we obtain a lot of measurements in real time. And those measurements are then used to identify the causal model through statistical learning techniques. And to ensure that this estimated model is accurate and that it covers the entire operating region of the system, we also perform active interventions in order to explore alternative operating conditions. So for example, we may temporarily adjust the routing configuration in the network and then measure and see how does that impact the response time of a service request, for example. And when we're doing these interventions, we are balancing two conflicting objectives. So on the one hand, we want to learn as much as possible about the causal mechanisms in our system. But on the other hand, we also want to keep the operational cost of the interventions relatively low. And later on in this talk, I will explain in detail how we address this particular trade-off in our method. But before I do that, I will start with a little bit of theoretical background, and I will introduce this formal framework of causality that we adopt in this work. And then I will use that framework to formally define the problem that we're trying to solve, namely the online identification problem. And then I will present our method for solving that problem, which we refer to as active causal learning. And after that, I will present a case study where we apply our method to identify a causal model of a service mesh that we run on our testbed. And finally, I will conclude and present the main takeaways of this research. So at the center of a causal model, we have a so-called causal graph, which encodes the causal structure of the system. So the variables in this graph correspond to, oh, sorry, the nodes in this graph correspond to system variables, and the edges represent causal dependencies. And here we distinguish between two types of variables. So we have exogenous variables that are shaded in the graph, and they represent external factors to the system. And we choose not to model the causal dependencies of those variables. And then we have endogenous variables that represent internal system properties. So to illustrate this distinction between these two variables, consider the following example, where we have a set of clients to the left that generate service requests, and then we have a set of servers to the right that make responses. And here we focus on three system variables. So we have the load in requests per seconds, the CPU utilization in percentage, and the response time in milliseconds. And in this example, it's very natural to model the load as an exogenous variable for two reasons. The first one is just, if you look at the architecture of the system visually, it's very clear that the load is external to the system, and it's not something that we can control internally. The second reason is that the purpose of the causal model is for optimizing the operation of the system. And when we operate the system, we don't really care about the causal mechanism behind the load. So the load may be high some days and low other days. And we don't really care about what caused the load to be high. What we care about is that if the load is high or low, how does that affect the behavior of the system? So for that reason, we model the load as an exogenous variable and the variables that are directly related to the system behavior to be endogenous. And the resulting causal structure is shown here to the right, where you see that the CPU depends on the load, CPU utilization, and the response time depends on both the CPU utilization and the load. And I would argue that if you ask a system operator or an engineer to construct this graph, they will be able to do that just based on intuition behind the system. So identifying the causal graph is actually not that difficult if you have the complete system configuration. However, the causal graph will only give you the causal structure of the system. It doesn't tell you the precise causal relationships. So for that reason, we complement the causal graph with so-called causal functions. For each endogenous variable, we have a causal function that determines its value as a function of the parents in the graph. So here we have CPU is a function of the load, and the response time is a function of the CPU and the load. Now, in contrast to the causal graph, the causal functions tend to be very complicated, and they can generally not be defined in closed form. So for example, the response time is typically a very non-linear and erratic function of the CPU utilization and the load. And for that reason, we typically need to identify these functions from measurement data rather than defining it based on domain knowledge. Now for the exogenous variable, since this variable does not have any parent in the graph, it doesn't have a causal function. So we model it instead with a probability distribution, a load distribution in this case. And taken together, this distribution, the causal functions, and the causal graph, we obtain a complete structural causal model. And the goal of the method that we have developed is to identify such a structural causal model of a particular network system that we are interested in. And now I will formally define this problem. So we focus here on general IT systems. And we model the IT system with an SEM. And we assume that the causal graph and the distribution of the exogenous variables are known. So as I mentioned before, the causal graph can typically be inferred from the system configuration. And if that is not the case, if you have a very complicated system and you may not even know the configuration, then there are also algorithms for discovering the graph from data. But that is out of the scope of this presentation. Now, the reason why we assume that the distribution of the exogenous variables are known is purely for ease of exposition. If you don't know this distribution, you can still use our method. But in this talk, I'm going to assume that it is known because it will just simplify the presentation and the notation quite a bit. What is not known, however, are the causal functions. And these functions may even be time varying. So as the system is evolving over time, maybe you're changing the service offering, you may be starting new nodes, retiring old ones, then your causal functions will also change. So from a practical point of view, the problem that we really want to solve is that we want to identify the causal functions online from system measurements. And by doing this online, we will be able to adapt our estimated functions to changes in the system. And we formulate this online learning problem as an active learning problem, where the goal is to select a sequence of interventions. Those interventions will then generate a lot of measurement data from the system. And using those measurements, we then want to estimate a sequence of causal functions that are as close as possible to the true underlying functions in the real system. And at the same time, we want to keep the cost of the interventions relatively low. So that is the problem statement. Now, to make this really precise, we need to also define mathematically what we mean with an intervention. And to do that, let us again consider the example system that we had before. And suppose now that we want to intervene on this system to control the CPU utilization. And this can be done, for example, by starting a compute-intensive script in the background or dropping some service request to reduce the utilization. And if we control the CPU utilization, that means that the CPU is actually no longer dependent on the load because we are controlling it. So the effect of this intervention in terms of the causal graph is actually that we can discard this edge here. So we obtain a new graph that we refer to as the mutilated graph. And this is now the causal structure while we are intervening on the system. And to represent this change in the causal structure mathematically, we introduce a special operator called the do operator. So when I write do capital C equals lowercase c, that is a mathematical expression for the intervention of controlling the CPU utilization to a particular value, lowercase c. And the benefit of being able to do this type of interventions on the system is that it will allow us to evaluate this unknown causal function here at specific input c that we are interested in. And the idea here is that by doing many of these evaluations at suitable input points, we will be able to learn or identify this causal function. So to illustrate this identification, consider the following example, where on the x-axis you have the CPU utilization, and on the y-axis you have the response time. And this function here is the causal function of the response time. Now, suppose that we are monitoring the system without intervening. So we're monitoring and we are measuring these variables, CPU utilization and the response time. We would then obtain a bunch of observations like this. And very likely, these observations are going to be confined to a small subset of the input space. And we refer to that subset as the current operating region. So in this example, the current operating region is when the CPU utilization is around 50%. And it's very clear from this figure here that if you just monitor the system in the current operating region, you will not be able to identify this causal function because you will not be able to see how the response time will be impacted if you have a very high utilization or a very low utilization. So that's exactly why we need to intervene on the system to be able to explore alternative operating conditions. However, such interventions, of course, also comes with a certain cost. And this is also quite nicely illustrated here because if you force the utilization to be high, your response time also goes up. And that can then degrade the performance of your users. So that involves a certain cost. In our problem formulation, we capture that cost by defining a cost function C. So for each intervention, we have a certain cost. And this cost function is completely system specific. So you can design it exactly how you want for your particular system. But that is only one part of our objective, to keep the cost low. The second objective that we have is that we want that the estimated causal functions are as close as possible to the true causal functions. And we capture that objective by introducing this loss function L. And this is essentially the mean squared error between the true causal function f and the estimated causal function f hat. So the precise formula here is not that important, but just remember that this loss function L captures the difference between your estimated causal functions f hat and the true causal functions f. And given that loss function and the operational cost function, we are now finally ready to state the problem that we're trying to solve, namely the online identification problem. So this problem is that we want to select a sequence of interventions and estimate a sequence of causal functions that minimize the discounted estimation loss and operational cost over an infinite time horizon. And the reason why we optimize over an infinite horizon is because we are trying to do this online. So it may be that the system will terminate at some point in time, but we don't know when that will happen or if it will even happen. So for that reason, we optimize over an indefinite time period. Now, unfortunately, if you look a little bit closer at this problem, you can see that it's actually intractable to solve for two reasons. The first reason is that we don't even know the true causal functions here in the real system. So it's not clear how you would evaluate this loss function. The second issue is that for most practical systems, you're going to have many variables, which means many causal functions, and which also means you're going to have an enormous amount of potential interventions that you can do. And that means also that from a computational point of view, this problem is generally going to be intractable. However, as I will explain shortly, our method will allow you to obtain a very meaningful approximation to this problem in a way that is also practical in the sense that you can actually run our method efficiently on an operational system, as I will detail now in the next few slides. So from an architectural point of view, our method can be understood through this diagram here, where we have three main steps. So first, we define the causal structure of the system. Then we use the available data to estimate the causal functions. And then we use active learning to select the next intervention to collect more data and then refine our estimate of the causal functions. So let me go through each step here. The first step is to define the causal graph. And like I mentioned earlier, this graph can typically be inferred from the system configuration. And the way you can think about this graph is that it defines a whole class of potential causal models, depending on how you define your causal functions. And within this class, we would like to identify the model that is most likely given the operational data that we have available. And we do that using Gaussian process regression. So we estimate each causal function with a Gaussian process. And in principle, you could use a different estimator here, but the Gaussian process has a particular advantage. And that is that for each estimated function, it will tell you where in the operating region are we most uncertain about that function. And that uncertainty then drives the intervention policy, which is based on rollout. So the way that this policy works is that it will evaluate interventions by looking ahead and seeing, okay, if I take this intervention, what is the operational cost and what is the expected information gain in my Gaussian process? And it will then select the intervention that, according to the look ahead, leads to the best outcome. Once we have selected the intervention, we then carry that out on the system and update or collect more measurements of the system variables, and then update the dataset. And then we repeat the same procedure again. So we do the estimation and then select the next intervention. And this iterative process continues during online operation of the system. So the way it typically looks like is something like this, where you start out with a prior of your causal function. You have a lot of uncertainty as given by the Gaussian process. And then gradually, as you perform interventions and you collect more measurement samples, you update your estimate and you reduce the uncertainty in different regions of the operating space. And to decide precisely where to intervene and where to collect samples at each iteration of this estimation, we then use the rollout intervention policy. And this policy can be understood through a look-ahead tree that we have here. So at each iteration of active learning, we have our current Gaussian process. That is our root of the look-ahead tree. Then we look for each intervention that we can do. What is the operational cost of that intervention? And how will that update the Gaussian process in expectation? And then we repeat this look ahead recursively until we reach some desired look ahead depth. And then we do a so-called rollout simulation, which is a very simple idea where we simply simulate the active learning process forward in time following a simple intervention policy, like a greedy policy or a heuristic policy. And then, after we have simulated some time steps into the future, we evaluate where we ended up in terms of the estimation loss and in terms of the operational cost. And then we backpropagate all of that information up in the tree and simply select the intervention that, according to the look ahead and according to the rollout, leads to the best outcome. So effectively, what we're doing here is dynamic programming, but with a twist that is more scalable, because we can now control exactly how many look-ahead steps we want to do and how many rollouts we want to do. And that will then allow us to adjust the computational complexity based on the available computing resources. So let us now illustrate this whole method on an example. So here we have a very simple structural causal model with 4 variables, and you see the causal functions here in the graph. And we will now apply our method to see if we can identify these causal functions only from measurement samples. And when applying our method, I will compare the estimated functions with the ground truth, and I will also compare it to a baseline method that we refer to as passive learning. So passive learning is equivalent to our method, except that it never intervenes. So it just monitors the system without intervening. And what you can see here in the top row is that our method identifies causal functions that are very close to the ground truth after around 30 measurement samples. By contrast, if you look at the baseline, it identifies the causal functions within the current operating region, but it fails to identify the functions outside of that region. And this limitation of passive learning is also very clearly shown if you look at the estimation loss. So here on the y-axis, you have the estimation loss, and on the x-axis, you have the number of measurement samples. And what we see here is that the loss of our method goes down very rapidly. And that is because the rollout policy is very effective in identifying interventions that drives down the loss. On the other hand, the passive learning baseline also reduces the loss a little bit, but it's so little that it's negligible in comparison, and you can barely see that the loss is actually going down here. And the fact that our method seems to work very well on this illustrative example and outperform the baseline is not just a coincidence, because there is actually quite strong theoretical justification for each step in our method. And all of these theoretical details are available in our paper, but I will just summarize the main results here. So the first result is asymptotic consistency, which states that as you update your Gaussian process with more and more data, it will eventually converge to the true causal function under certain regularity assumptions. And this is a well-known result in Gaussian process theory. The second result is that the mean of the Gaussian process will minimize the loss function L that we defined. And we prove this in the paper. So in other words, the mean of the Gaussian process is the best possible estimate that you can obtain given the available data. And finally, we also show that the rollout intervention policy will improve upon the greedy policy without look ahead under general assumptions. So in other words, there is a benefit for doing this look ahead optimization. It will lead to a better intervention with a lower cost and lower estimation loss as well. So that concludes the description of our method, which we refer to as active causal learning. And now I will present some experimental results of applying this method for identifying a causal model of a service mesh on our testbed. So the target system that we run on our testbed is illustrated here, where we have a client population that generates service requests. Then we have a web server that provides web services, and those services are supported by a service mesh backend that run microservices, which are implemented in Kubernetes and Istio. And in particular, this service mesh consists of 4 physical nodes that run 3 different types of microservices, M1, M2, and M3. And collectively, these microservices provide 2 different web services. Service S1, which is an information service that invokes M1 and M3, and service S2, which is a compute service, which invokes M2. And the way you can think about a service request here is as a traversal of this graph. So a request for service S1 can either be routed through node 1 and node 2, or through node 3 and node 4. And similarly, the request for S2 can either be routed to node 1 or node 3. And the control variables here are the CPU allocations for node 1 and node 3. So we have vertical scaling of those nodes. And then we also have the routing probabilities, which determine the fraction of requests that are routed to node 1 versus node 3, and the blocking probabilities, which determine the probability that a service request will be blocked here at the front node. So we would like to identify now a causal model that tells us precisely how changing these control variables will impact the response time of a service request, because that will then allow us to optimize the system to meet management objectives. And to this end, we define the causal structure of the system using this graph. So here, all of the control variables are exogenous. And we also introduce two noise variables, epsilon R1 and epsilon R2. And these random noise variables are used to model the fact that the response time of a service request is typically not going to be a deterministic function of the control variables, but rather it's going to be dependent on random effects in the system. And we can model this using these noise variables. Finally, we also have the load variables, which also are exogenous. So the requests per second for service 1 and service 2. Now for the endogenous variables, we have the response times R1 and R2, and we also have the carried loads. So the carried load is the non-blocked load of each service, which is why you see that the carried load has a causal dependency on the blocking probability. And the main striking feature about this graph, when you look at it, is that the response times depend on a lot of factors, unfortunately. So, for example, the response time of service 2 depends even on the load of service 1, since they share the underlying hardware infrastructure. And that makes it, the causal dynamics are quite complicated for the response times. And we would now like to identify the causal functions that define each of these edges here, each of these causal relationships. And we would like to identify them only from measurement data collected when the system is operating. So for the evaluation, we will consider two different evaluation scenarios. In the first scenario, we load service S1 with 4 requests per second and service S2 with 15 requests per second. And the loads are kept constant throughout the entire evaluation. So in this scenario, the causal functions will not change, they will remain fixed. Then in the second scenario, we focus only on the second service, S2. So we have a smaller causal graph where we only have the variables related to S2. And we load this service with 1 request per second. And then we divide the evaluation scenario into 2 time intervals, where in the first interval, we run only the service S2. But then in the second time interval, which starts at time 11, we start the other service in the background. And that will then have the causal functions of service S2 to change. So the causal function will be non-stationary in this case. And this will allow us to investigate how our method can adapt to such changes. And to estimate or evaluate the performance of our method, we also need to have access to the ground truth, to the real causal functions. And for this purpose, before we do the evaluation experiments, we do a very lengthy monitoring phase of our system, where we monitor it for several days and even weeks to collect a lot of measurement data of all of our system variables. And that then allows us to estimate here the ground truth causal functions. And this is just a subset of the causal functions. So the main thing just to take away from the ground truth here is that the causal functions are quite complicated and they are not simple linear relationships. Especially the response time as a function of the load is very complicated. And here is the correlation matrix of the data that we collected. So the correlation, the Pearson correlation between all system variables. And most of the correlations here are as you expect. But one thing to remark is that we also have some correlations which are not causal. So for example, the load of service 1 is correlated with the load of service 2, even though they are causally independent in our graph. So this just illustrates the fact that causation and correlation is not the same thing. And for the evaluation, we also define the cost of the interventions to be as follows. So clearly, the cost of not changing anything in the system is the lowest cost. And then we define the cost of the other interventions to be roughly how much effort is required for doing the intervention. So for example, changing the routing probability in Istio is very simple, so very little effort, whereas emulating the service load can be quite complicated, so that has a higher cost. But in principle, you could define this cost exactly how you like for your particular system. And here are then the evaluation results. So we start by looking at the passive learning baseline. And this baseline performs very poorly on this system. And the reason is that passive learning allows you to explore a very tiny, tiny region of the operating region, tiny, tiny subset of the operating region, which means that you're not really able to identify the causal functions. So you see that all the measurement samples are centered at specific points here. By contrast, if you look at our method, it allows to obtain much better estimates of the causal functions. It's not perfect, but even after only, say, 30 measurement samples, we have a pretty good understanding of the causal dynamics in the system. Much better than the passive learning baseline. And we can zoom in on one of these causal effects. So here we have the causal effect of changing the blocking probability on the response time of the second service. So you see how the estimated causal effect evolves over time, where in the beginning we have a lot of uncertainty, and then gradually as we collect more and more measurement samples, the uncertainty reduces and we become closer and closer, we obtain a better and better fit of the true causal function. You can also note here that some measurement samples are not in line with the true causal functions, and that is because we have measurement noise. So there's quite a lot of noise actually on the real system on the testbed. So that also complicates the estimation. But as we showed in the theory earlier, as long as you have enough measurement samples, it will eventually converge to the true causal function. And this is also shown if we look at the estimation loss. So similar to the trend we observed before, we see that our method very rapidly reduces the estimation loss. And that is because it's able to pick interventions that greatly improves the estimate of the causal functions. Whereas the passive learning baseline remains with a very high loss. That reduces a little bit, but it's so negligible that it's not even visible in the figure. And if we look at the second scenario, where we have changes in the causal functions, so here we see the causal function for the response time in function of the routing probability. And you see that before the change, we have identified a function that is very close to the ground truth. But when the change happens here at time 11, then our estimate becomes inaccurate again. But then the interesting thing is that you can see that our method automatically adapts to the change and very quickly starts updating the estimated causal function, increasing the uncertainty due to the changes in the data distribution, and then gradually adapts the estimates to fit the updated function. And after only, say, 10 samples, it have fully adapted to a very close approximation of the true updated causal function. And this is also shown if you look at the estimation loss, where we see that our method reduces the estimation loss very quickly in the beginning. Then when the change happens, it goes up again, but then it gradually starts going down. So we have this automatic adaptation of the estimated causal functions, which demonstrates the benefit of having online learning as opposed to offline. So in conclusion, we believe that causal models can enable us to build network systems with a higher level of automation, reliability, and predictable service quality. And we have developed a new method for online learning of causal system models, which consists of three main steps. So we define the causal structure in a causal graph. We estimate the causal functions using Gaussian processes, and we collect more data using a rollout-based intervention policy. And we have shown that this method has appealing theoretical properties, and we have also validated it experimentally on a service mesh. So thank you very much for your attention.